Hello from Turkey. We are GTU ROVER team, proudly representing Gebze Technical University. We are excited to introduce Fatih, our next generation robotic platform. Engineered and optimized to meet high operational standards of the ERC 2026 competition. Since 2020, our mission has focused on accumulating advanced space robotics and engineering knowledge to maximize field efficiency. Our organization brings together 40 qualified students structured into 5 subteams: mechanics, electronics, software, science and business. Our primary objective this year is qualify and compete in the European Rover Challenge 2026. As young engineers driven by Turkey National Space Program and Future Learner mission, we aim to bench test our technological innovation and expand our field expertise.
The mobility system is designed to reduce vibrations and shocks in rough terrain, ensuring a smooth and safe drive. The chassis is made of 2.5 mm thick carbon fiber composite material. The composite panels were manufactured using the vacuum infusion method and precisely cut using water jet technology. They were then assembled using aluminum brackets. The battery pack is mounted under the chassis to keep the center of gravity center and protect the batteries from external influences. The rover has been fully optimized for driving on rough terrain using a rocker suspension system. The 4 airless wheels used on the rover are specially designed, each measuring 27 cm in diameter and 10 cm in width, and they enhance the rover's drive comfort by absorbing variations. The rover has a total length of 95 cm, a wheelbase of 70 cm, and weighs approximately 56 kg.
In the unforgiving conditions of Mars simulations, the mechanical strength must be guided by an advanced controlled intelligence. At the core of our drivetrain, an STM32 microcontroller processes movement commands with high-speed precision, while RoboCloud 2X45 motor drivers channel power to the wheels. Equipped with AMT103V incremental encoders on each wheel, we capture real-time velocity and positioning data with millisecond accuracy. By processing this live data through our custom-developed PID algorithms, we achieve seamless starts, smooth declarations, and fluid navigation dynamics.
The entire rover is orchestrated by a ROS2-based software architecture. Every subsystem has its own dedicated package with the nodes, parameter files, and launcher files, allowing each component to be developed, tested, and upgraded independently. Before any package is deployed to the real rover, it is first validated in a Gebze simulation environment. For teleoperation, we use 2 parallel control pads. The first is a joystick, one for driving, one for arm control, publishing velocity commands directly to ROS2 topics which are received by the GTU. The second pad is a React-based web GUI connected to reverse bridge. It requires no ROS2 installation, it runs on any laptop. Our ground station uses multiple laptops on a network switch, each with a dedicated role, cameras, arm control, task management. For autonomous navigation, we use IMU, wheel encoders, and ZT visual odometer through an extended Kalman filter. This is our top map for real-time lab, which now uses for path planning and obstacle avoidance. During the traverse subtask, the rover navigates fully autonomously. No video feed, no GNSS sent to the ground station.
A relentless mission demands an unyielding power source with an uncompromising approach to the system safety. Driven by a robust 6 series configuration, 24 volts, 32 amp-hours battery, our rover comfortably sustains over an hour of continuous high-load operation on a single charge. To guarantee absolute structural safety, our hardware emergency stop utilizes a heavy-duty automatic relay backed by a blade fuse, providing an instantaneous, reusable mechanical brake in the power line. As a secondary security layer, we integrated a software-level kill switch. To perfect this architecture, we rely on custom-developed electronics. From our battery management system and voltage regulators to our custom point-to-point routed carrier boards for microcontrollers and power distribution, we maintain total control over our hardware ecosystem.
In remote operations, a rover is only as capable as communication link. To guarantee unbroken control, we engineer fail-safe multi-tier network architecture. We utilize a 2.4 GHz network equipped with Rocket M2 routers and 120-degree sector antennas, operating alongside a high-speed 5 GHz network. This robust setup guarantees ultra-low latency, seamlessly translating operator inputs into instantaneous movement at distance well beyond 100 meters. To achieve total visual dominance and eliminate blind spots, we strategically deploy 3 different camera technologies: IP, USB, and a dedicated 5.8 GHz FPV. Our 5 GHz band is connected directly into the jet sonorin, exclusively handling critical telemetry, movement, and payload commands. Conversely, the 2.4 GHz network is routed through a network switch solely for IP video streams.
A 5-axis robotic arm was utilized to execute the manipulation tasks. A DC motor with an L-type gearbox was implemented on the first axis, featuring a 1:30 ratio self-locking worm gear mechanism for motion transmission. On the second axis, a cycloidal gear mechanism with a 1:36 reduction ratio is used to reduce backlash and minimize efficiency losses caused by friction. The movement of the third axis is provided by a worm gear system integrated into the DC motor. Operational safety is ensured by the worm gear's self-locking mechanism. Actuation of the fourth and fifth axis is achieved by a differential wrist mechanism featuring powder bed fusion-printed gears. Soil sampling and manipulation tasks are performed by a specialized gripper, actuated by a DC motor and worm gear mechanism. The use of TPU-lined fingers ensures a secure and high-friction grip. The structural connection between axes consists of carbon fiber tubes, while the joint interfaces are constructed primarily of aluminum. The final assembly yields a robotic arm weighing 30 kg with a total reach of 1.2 meters.
To drive our robotic arm, we utilize 3 RoboClaw 245 controllers.
In complex manipulation tasks, true dexterity requires a highly optimized and elegant electronic architecture. All drivers seamlessly interface with our Jetson O-ring computing unit over a single shared UART line. By pairing this clean architecture with continuous encoder feedback and precise PID tuning, we eliminate mechanical jitter and achieve millimeter-perfect positioning.
For the drawing subtask, GTU ROVER presents a reliable and full automated aerial platform.
With a take-off weight of approximately 3 kg and a 6000 mAh battery, our unmanned air vehicle ensures a 10-minute flight time, carrying a Raspberry Pi camera as its primary vision payload, while utilizing commercial off-the-shelf components like the Pixel and actively monitoring telemetry via Mission Planner. All hardware integration and MATLAB Simulink-based algorithms were executed entirely by our team.
Furthermore, the system is fully protected with an integrated fuse and a master circuit breaker to ensure hardware safety.
Moving on to flight dynamics, the drone takes off smoothly, maintaining full stability across all 6 axes, up, down, left, right, forward and backward before safely landing.
Safety is a strict priority. We can instantly trigger an autonomous emergency landing via a dedicated switch on the RC.
The drill system is designed to collect soil samples from a depth of 17 cm below the surface. The system consists of 2 primary stages. In the first stage, the desired depth is reached through vertical movement. In the second stage, the auger makes contact with the surface and ensures the preservation of the soil sample within its surrounding aluminum tube. The container system, which operates in conjunction with the drill system, is mounted beneath the chassis. The system, which is moved out from under the rover using a linear actuator, contains 2 containers equipped with internal weight sensors. The lift system located under the chassis prevents contamination and ensures the safe transport of the samples. The liquid collection system comprises a 2-component structure consisting of a peristaltic pump model and a leak-proof container produced by FDM technology. The pump is mounted on the chassis. One end of the pump is secured to the tip of the drill mechanism, whilst the other end of the tube is connected to the leak-proof container on the chassis. The container is fitted with an O-ring seal to ensure leak-proofing. A pH meter is integrated to the leak-proof container to provide real-time pH measurements of the collected liquid.
Whether the arm is executing highly sensitive operations like flipping switches and pressing buttons on a control panel, our electronics guarantee smooth, highly responsive manipulation.
Extracting precise scientific data in the field demands highly synchronized and resilient electronic architecture. A third of our onboard laboratory is a decentralized architecture powered by ESP32 microcontrollers, configured as 1 master and 2 slaves. This setup efficiently distributes processing tasks, aggregating all vital sensory data before streaming it to our central Jetson O-ring. This robust electronic framework is responsible for the complete control and data acquisition of our payload. It seamlessly drives and monitors our entire suite of scientific instrument, including atmospheric sensor, load cell, the core drilling mechanism and the pH meter. This module actively controls our core drilling mechanism, providing rapid response to remote commands.
For the ERC 2026 mission, our scientific objectives centered on geological exploration and habitability assessment within the Hellas Planetary region. We conducted a detailed analysis using orbital datasets, scientific literature, and digital mapping tools including JMARS, MarsTrack, and Google Earth Pro to identify key exploration zones. Based on this analysis, we developed a mission-specific geological map to guide our exploration strategy and optimized rover transversal. To evaluate our primary scientific objectives, our science payload combines atmospherical and soil analysis with contamination-aware sampling strategies.
We continuously monitor methane, carbon monoxide, and carbon dioxide concentrations to investigate local environmental conditions, while integrated pH analysis provides insights into the chemical properties of collected material. By comparing surface and subsurface samples obtained through our drill system, we aim to identify meaningful compositional differences.